So, testing of memories is, testing of systems is therefore becoming an important aspect. So, a lot of different technologies have been developed to test a chip or test the entire system. So, the first thing we talk about is in situ testing. So, if I have a big PCB, and let us say there are many chips which are already present on this. See, we would have tested the packaged ICs before inserting them into the PCB. So, we only known good ICs. But then these guys will be connected, right? There will be PCB traces which are running to interconnect these guys. So, we have to worry about interconnects. There could be some open faults, or there could be some short circuits. So, these are the typical problems that the interconnects may have. The IC testing itself we have discussed already, right? Digital ICs, analog ICs, mixed signal, memories. So, the techniques that we have already discussed will apply there. But now, the PCB itself has to be tested, number one. That means we are worried about these interconnects becoming faulty. But more importantly, these ICs that are inserted into the chip, inserted into the PCB, what if an IC fails over time? So, maybe this developed a problem little later. It was good when we inserted the IC into the PCB, but after a few months or years, it has developed a problem. So, when the board, the IC fault will be visible when the PCB does not function correctly. And many PCBs may be sort of connected in one big system. So, you see the fault could be anywhere, it could be in any one of these PCBs, and it could be in any one of the chips inside this PCB. So, we have to isolate where the fault is. Then we may be able to repair the system. See, unlike ICs, PCBs could be repaired. See, if the IC is bad, we really cannot do much. We have to throw it away. But in the PCB, if one of the ICs has gone bad, it may be possible for you to remove that IC, place a new one and make it work. So, that is what people would like to do. They would like to, but then there may be several ICs on the same PCB. So, if a PCB is not working, you have to debug. You have to understand which one is bad, which circuit is bad. So, which means we need access. Okay, so if there is a big PCB, we need to be able to provide test access, need a test access mechanism. And we need in situ testing, meaning you should not tell me to remove all the ICs and then test all of them and then insert them back. Okay. So, that is not an acceptable solution. We cannot remove the ICs, separately test them, and detect which one is faulty. So, this is not a solution. So, we have to have a test mechanism which sort of gives me access to this. It is as though we should have the we should get the feeling that we have full access to all the inputs and outputs of the IC. So, that is the feeling we want. That is what is in situ testing. Test it in its own place. Similarly, if there are many PCBs in a bigger system, you should not ask me to sort of remove all the PCBs and then test. It should be possible for you to apply a test for a specific IC in a specific PCB, by getting full access to that. So, get test access to any board and any IC. So, that is what we would like. So, if I have an IC here, I would like a test access mechanism. So, I should be able to send test signals and I should be able to observe responses. So, that is what is the aim, right. So, this has been done with the help of certain standards. So, standards are important. So, a long time ago, they developed what is called as a bed of nails testing. So, here is an example of a bed of nails test fixture. So, the PCB will be sort of placed on top of this bed of nails, and as a result you get direct access to those points where you want to apply a signal or measure the output. Okay. So, people do use them, right, but that is somewhat. So, what they have done is they have developed a standard called boundary scan. So, when they design the IC, so there may be the core of the IC. This is the core logic, or it includes all the electronics inside, right. Plus, there are some inputs and outputs, isn't it? This is an input pin. There may also be some output pins. So, let us pretend that these are the inputs and the outputs. There may be another IC sitting on the PCB with pins on this side, and these may be driving this, and there may be another another IC here with some core logic here, and these may be the input pins, and these guys could be driving them. So, these wires are on the PCB. So, these are all the wires on the PCB. So, in the normal mode, the this particular core will send data to this core, and this core may send data to this core, things like that. So, they are working like this in the normal mode. Now, if I want to activate a fault here, suppose it is a digital core and I want to apply a stuck-at fault here, I am sorry, apply a test for a stuck-at fault here, then the ATPG tool will tell me that you have to apply signals to these input lines. Okay. Maybe one of them is a scan chain. So, the test tool will tell you to bring inputs and then sort of scan it out and then capture the response, and then all that you will have to do. Okay, but unfortunately you don't have access to these pins. Okay, these pins, this is not accessible. Internal pins cannot be observed or controlled. So, a very clever solution has been to use what is called as a boundary scan. So, this IC this IC this is a core logic. So, instead of having a pin to bring the inputs, they will replace it with what is called as a boundary scan cell. Okay. So, BSC stands for boundary scan cell. It has some flip flops where we can store the input. Similarly, there is another boundary scan cell maybe here, and another one here, and a fourth one, fifth one. So, each pin, whether it is input pin or output pin, will be replaced with a boundary scan cell. And these boundary scan cells have a primary input and a primary output, but they also have a scan input and a scan output. So, the scan input of the boundary scan cell will be connected like this. So, now the advantage would be, if I want to send some value to any one of these wires, I can depend on the boundary scan cells. So, we can connect all BSC boundary scan cells into a scan chain. I am not referring to the scan chains which are inside the core. These scan chains are different. I am talking about a separate boundary scan chain. So, now if our test requires us to scan some values through this boundary, through this scan chain, I can use this path. It will give me test access. Similarly, if I want to put some value in this particular pin so that I can drive this particular output, in this particular input, then I can use this boundary scan chain and put that value here. And if I want to observe some value, let us say normally the value of the core gets latched here in this pin. If I want to observe what was connected, I can use this particular path. So, I hope that point is clear. So, let me show you a diagram. This diagram that I have drawn may not bring out everything. So, let me show you a boundary scan cell. It is called boundary scan because it is in the boundary of the chip. Okay. So, here is a picture of the boundary scan. The boundary scan cell looks like this. So, this is the input coming from the outside world, and this is what connects to the core. So, this is the outside world is coming and feeding this particular pin, and the pin is in turn feeding the value to the core. So, this is how it is done. The value of the input can be captured into these flip-flops. Okay. So, you can take this parallel input coming in and you can sort of this acts like a master slave flip-flops, capture and update. So, you can capture it into this cell. Similarly, the input, the value stored here can be used to drive the parallel out. So, the value stored here can drive the core logic. So, you can either drive it directly. Okay. In the normal mode, maybe you want direct, the input coming here should go directly to the core, but in the test mode it will be this guy. In the test mode you want this to drive. Okay. So, the boundary scan cell can be seen to have 4 pins, parallel in, parallel out, serial in, serial out. There is also a what is called a small controller called a test access port, which can be used to control the operation of this boundary scan chain. So, if there are multiple cores on the chip, maybe one of them is a TI DSP, the other could be some other core logic, etc. So, this is one chip on the IC, this is another chip and a third chip, etc. The boundary scan will have 4 pins called test data input, then there is a test data output, test clock and test mode signal. The test mode is if it is 0, that means we are in the normal mode of operation. If it is 1, that means we are in the test mode of operation. In the normal mode of operation, the data will flow like this. It will the primary data coming from the outside world will go in. So, in the test mode of operation, the test data is scanned in. In the normal mode of operation, it is this normal mode data that goes inside. Okay. So, I hope that point is clear. So, imagine that this is a PCB with 3 chips. Okay, this is a PCB with 3 chips. I may want to test this particular one, let us call this as A, B and C. I want to test chip number B. So, how do I do that? I will go into the test mode and use this path. If I go all the way, then unfortunately, it is a waste of time. I really do not want to go all the way. So, there is a bypass mode. So, you can bypass and directly come out, and you can fill the value that you want, and again here you can bypass and come out. So, bypass is used to avoid having to take a long path. Okay. So, if there is a scan chain here, let us say there is a scan chain here. If I want to initialize that, then again what will I do? I will take this path. So, it gives me a mechanism to fully get access to the inputs and outputs of the pin. Okay. So, that is the beauty of this particular design. So, I can do in situ testing. So, I may start by saying first let me test chip A. Okay. So, there you will go through this mechanism. So, you will select test mode signal to be 1, right. This will be made 1, and then the test clock will help you to move the data from TDI to TDO, bypass and come back. If you want to access the scan inside, you can start with TDI, go through the scan chain and come back, bypass and come back. So, test A, then test B, test C. Okay. So, you can test all the chips one by one. It will take time because you have to slowly go through the TDI and TDO, etc., etc. But it will allow you to do it. So, originally the JTAG or the boundary scan, okay, it is also called as JTAG. JTAG means joint test action group. So, as the name suggests, companies belonging, or rather experts belonging to different companies, they all came under this group. Okay, they formed a group because before all this boundary scan etc. was invented, what used to happen was on the PCB, they used to use ad hoc methods to test the PCB. Okay, there was no systematic way. So, ad hoc test means here is one chip and here is another chip. So, see if C1 can test C2, things like that. So, each sort of testing of every PCB was separate and there was no standard. See, such a solution becomes very difficult to practice. Okay. So, these ad hoc methods have been converted into a very straightforward and simple mechanism which can be repetitively applied. Okay. So, JTAG was a standard that they proposed and later IEEE accepted it, IEEE 1149.1 standard, that is same as JTAG. It's everybody refers to it as a JTAG. So, you know how to get full access to any one of the chips using this method. The other thing that you may be interested in is how to test the interconnects, and like I was just telling you, this JTAG is also useful in debugging. That was not the original purpose, right? The original purpose was to test, but it can also be used for debugging. For example, let us say inside this there may be several registers. And these registers are part of a scan chain anyway, right? Now, imagine that I have to place a specific value in R1. So, I can sort of use this scan mechanism that I just described and go and access that particular register, fill whatever value you want and then come back. So, in other words, we can initialize a register to whatever value you want. Similarly, you can shift out the contents of that register and display it. Okay. So, let me draw that here maybe.